And so our study area is in Idaho. It's a reference point on the Boise River. This is a USGS stream gauging station is our reference point. There's 3 snowtail sites we looked at in this basin: Jackson Peak, Atlanta Summit, and Bogus Basin. And on the map here, this is all the snowtail sites in the state of Idaho. And our reference point is the Boise River, just east of Boise, Idaho, in this watershed, about right here. This is a kind of a Google Earth map of it. Here you see Boise, Idaho. Boise River comes up right here. This is right about here is our USGS stream gauging station, which is our reference point. The snowtail sites, Jackson Peak, Atlanta, and Bogus Basin, they are in the alpine areas where the snowpack occurs in this watershed. And so, as I mentioned, the Stevens Hydroprobe, manufactured by Stevens Water Monitoring Systems, is the soil sensor used in this network. And in my company, Stevens Water, we're committed to helping the NRCS fulfill their mission, which is providing high-quality data for these forecasters in this water supply forecast. And so I'm going to skip over a couple slides here. So before we continue, I just want to maybe explain a little bit about soil physics and what we're doing here. And so in soil, or in water in general, there's a phenomenon called capillary forces. And it's the capillary forces is the force that holds water in the soil. And capillary forces results from the surface tension of water at the air-water interface. So from a chemical perspective, water is a very polar molecule, and air is essentially a non-polar. And so the water wants to get away from the air, and so a tension develops at the air-water interface. And we see this in a meniscus. This is why a meniscus occurs. There's surface tension, and the water wants to relax, and it climbs the walls of a capillary. And so the same thing happens in the soil. In the soil, there's microscopic pore throats. The water will get itself into the smaller pore throats to eliminate that surface tension. And that's essentially the force that holds the water in the soil. And so we can move to this graph here on the x-axis here. We have soil type. So as you move to the right, you get more clay-rich. On the y-axis here, you have soil moisture. And so as you get more clay-rich, the soil water retention characteristics change. We have a parameter called the field capacity. And the field capacity is the point at which the capillary forces can no longer hold the water in the soil. The soil gets so saturated or wets up to a point where gravity can then exceed capillary forces and then pull the water downward. And so this is called a soil water retention curve. And so here you have on the y-axis, soil moisture is a fraction. And on the x-axis, you have the unsaturated matrix head of the soil. And what that is that's the amount of pressure it takes to pull water out of soil. And so this is called a soil water retention curve. And of course, it changes with soil type. So this curve also has inflection points. And so one of the inflection points, and the slope of that inflection point, is what's called the field capacity. And again, that's where the gravity and the capillary forces sort of equal one another, and that's the point at which water in the soil will flow downward and recharge the saturated zone. And also, it's important to note that from this curve, you can infer a lot of things. You can take the inflection points, the slope of these inflection points on this curve, and calculate things like the unsaturated hydraulic conductivity and other hydrological parameters that allow you to get the infiltration rate and volumetric flux of the soil. And so we characterize the soil at each of these 3 snowtail sites. And so the last column here, this is the what's called the field capacity again, and it's the inflection point on that previous graph that I talked about. And it occurs normally about 333 hectopascals of head. And so this is the water content at 333 hectopascals. And this will make sense on this next diagram. So what we're trying to define here is the soil moisture deficit index. And the soil moisture deficit index is essentially how much more water you can put in the soil before it flows out. So if you think of soil as being like a bucket, and there's a hole halfway up the bucket, and there's some water in the bucket, and the hole represents field capacity, and the top of the bucket is saturation. So if you fill the water up to the hole, it's going to come out the hole. And if you keep filling it up and if it overflows, that's saturation. So the soil moisture deficit index from the soil survey and also the real-time soil moisture readings, we're going to get, it's basically the amount of water you can put in the bucket before it flows out. It's how much more water the soil can hold. And it was calculated by the average soil moisture in the column, measured with the soil moisture sensors, minus the calculated field capacity in the soil survey. And we get what's called beta DI, the soil moisture deficit index, and that's our modeling parameter. And so we modeled the data. This is for the this is the soil moisture. The top here is the average soil moisture in the column. The graph below is the soil moisture deficit index. And this is for one of the snowtail sites. This is for the Atlanta snowtail site. And you can notice that there are seasonal trends here, seasonal oscillation of soil moisture that we can observe. And this is true for most snowtail sites in the U.S. And so we have in the wintertime, you have this flat line. The soil moisture doesn't really change very much in the winter. And you see from winter to winter, it's a flat line. And you know, from year to year, it can be different depending on what your fall precipitation is. And then it stays relatively constant. And in the spring melt, you see the soil moisture go up to a point, and then at some point during the summer, when the snow melt, when the snowpack is gone, you see the decline of soil moisture going all the way down. And then about September every year, or October every year, before the water year begins, you have the lowest point. This is the driest point of the year. And you see this trend year after year of a flat line in the winter, the spring melt, and then the summer dry, and then the fall recharge again. And so this is the modeled results after we ran the simulations. The black line is the observed data from the USGS stream gauging station. The light blue line, which is just kind of difficult to see here, is that is the historical forecast. So this is the historic forecast product from the NRCS. And so the green line here, this is the modeled stream flow forecast with all of the parameters. So taking into account the meteorological parameters, the antecedent stream flow, and the new soil moisture deficit index. You can see that it is, towards 2008, it does improve significantly. This blue square is the model simulation results where we're just modeling the soil moisture deficit index as a standalone. And you can see that as a standalone, it's not very good. But if you add it with the other input parameters, the stream flow, the antecedent snowpack, it improves significantly. And it's also important to note that this kind of statistical correlation, you need about 17 years of data in order for the model to run properly. And so these soil moisture sensors were installed in the late 90s, so it's just now we have enough data over this whole, over several decades now that allows us to have a stable simulation in the principal component model. So this is another simulation here where we can see the difference that the soil moisture deficit parameter makes. Here we see the red is the historical forecast using just the meteorological parameters and the and seeping stream flow. The light blue line is the actual river data from the USGS site, and then the blue line is the new forecast with the added soil moisture deficit index. We can see here, starting about 2009, does improve quite a bit. And so this is just some raw data. And so here we have the percent contribution of the soil moisture deficit index. So right around 3% for Atlanta side, but was based on the Snowtell site, 5%, and also Jackson Peak Snowtell site. It contributed 5% to the forecast. And if you add them all up, the soil moisture deficit index contributed about 13% into the inputs for the model. And so this table here just is a percent improvement that the soil moisture data made over the historical forecast. 2005, we didn't have data. And starting about 2001, when we had enough data to run the simulations. Some years are negative, so it doesn't always help. But as we start about 2009, it really starts to look good. In 2010, it improved it by 24%, which is pretty significant. And so here's some improvements to our methods. One, we have some missing data sets. So we can, to improve these simulation results, we could potentially model where we don't have soil moisture data. We can model it using a numerical model called Hydros-1D. And we can take the meteorological parameters and run them through this model and forecast and predict what the water content would be, and then we could use that as an input into the principal component forecast model for the stream. The second thing we could do is we could do more of a weight average of the soil moisture deficit index. Here we just average the soil moisture in the entire column, but we actually have soil moisture at different depths within the column, and we could do more of a weighted average of that to improve the accuracy of the soil moisture deficit index parameter. And then thirdly, we could add more Snowtell sites or add more soil sensors in the basin to improve the accuracy of the forecast. And so in conclusion, accurate water supply forecasts are critical. The soil moisture under the snowpack represents a large reservoir for water. Soil moisture data measured with the hydroprobe soil sensor was modeled along with the meteorological parameters to provide a stream flow forecast. And then implementation of the soil moisture data could potentially significantly improve the forecasts. And so I want to acknowledge my colleagues here, Deb Harms from the USDA. She managed the soil moisture data, or the soil survey data. Jolene Lee, she's the forecast hydrologist that ran the simulations. She's with the USDA and RCS. I'd like to thank the Snowtell program, all the people there at the NRCS, and also Stevens Water Monitoring Systems. So with that, I'll take questions.
From your slides, it looks like you only have one type of sensor, like a GDR, to measure water content profile. But in order to determine the filter capacity, as you mentioned, we determine using the 1/3 of bar to determine what kind of water content for the size of the filter capacity. So I don't know how you get the water filter capacity without the suction or water potential sensor.
Well, the field capacity was measured in a lab. So soil cores were taken, field capacity was measured by the pressure at which the water kind of came out. There's an apparatus for that. And that was done in Nebraska at the National Soil Lab. So that field capacity value